Assalamualaikum and a very good day to all of you. So for today's session, you will be learning another analytical instrument applying the principle of spectroscopy. Atomic absorption spectroscopy, or in short AAS, is a sophisticated technique to measure the concentrations of elements in a sample by observing its electromagnetic spectrum. So during this lecture, we will explore the fundamental principle of AAS, including the instrumentation, processes, calibration, and the diverse applications of AAS in fields such as environmental science, clinical analysis, pharmaceuticals, and industrial quality control, etc. All right, so please bear with me throughout this lecture session. So before we dive into the interesting topic of AS, let's take a moment to refresh our memory on some key concepts we have covered previously. I hope you still remember our discussion on spectroscopy, where we explore the interactions of electromagnetic radiation with matter. And you also learn the UV spectrophotometer and the fundamentals of Beer's law or Beer-Lambert's law. Alright, where you have the linear relationship between absorbance and concentration of an absorbing species. Alright, so these concepts are crucial as they form the fundamental for what we will be learning today for the AAS. Now let us see the general information of AAS itself. AAS, or atomic absorption spectroscopy, is a powerful analytical technique that helps us measure the concentrations of different elements in a sample. I bold elements there because it is an elements that you can find in periodic table. Right? So this technique is incredibly sensitive, where it can detect even tiny amounts of elements down to part per billion. What really interesting is how it works. It uses specific wavelength of light that are absorbed by each of these elements. So the wavelength correspond to the exact energies that needed to move electron from one energy level to a higher one. So this way we can accurately identify and measure the element present in our sample. Now, let us see what are the things that we can analyze. AAS, a method we use to analyze both metallic and non-metallic elements found in all sorts of stuffs, whether it is inorganic or organic material. Think of it as a way to figure out what elements are present in a sample. Let's say you are having your ikan bakar for lunch, and that ikan bakar was wrapped by aluminium foil. So thus the aluminium contains in a flesh of ikan bakar. So you can check, okay, the aluminium atoms, is it present in the ikan bakar flesh? Or you are having your water now, you are drinking a water, and think either that water contains lead, okay, the plumbum. So how much is the concentration of plumbum contains in your daily drinking water? So you want to know it, you can measure through AAS. So if you refer to the periodic table here, okay, more than 70 elements in yellow shaded. All right, I shade the periodic table in yellow. So that one is actually elements can be detected by AAS. So how does it work? So basically, we are talking about atoms in a gaseous state float around freely. This is in the machines itself, spectrophotometer. So basically, you will have your solutions ignited and in a gas form, so it floats freely. When we shine lights through these gases, some of those atoms absorb specific wavelength of light. It likes they are picking certain colors from the light spectrum, and now by measuring what light gets absorbed, we can tell which elements are present in our sample. So it's like a unique fingerprint of each element. And but now, how do we know how much of each elements in there? So that's where calibration comes in. We start by preparing solutions with known concentration. So those who have done their labs on calibration for UVVs, a similar calibration process can be done with the AAS, where actually the concentration of the calibration solutions is based on our target element. If you are targeting of looking into plumbum, so you'll be doing the standard solutions for plumbum. If it is for aluminium, you are doing the standard solutions for aluminium. All right, so having these standards, and you are running the standards through AAS instrument, okay, atomic absorption spectrophotometer, you will create a working curve. We call it as calibration curve. So this curve helps you relate the amount of light absorbed to the concentration of the element in the sample. Get it? So now, why do we bother with all this, right? So well, in analytical chemistry, knowing the concentration of different elements in a sample is crucial. Let us say we are testing water for pollutants or checking the nutrient content of soil. So AAS help us pinpoint exactly how much of a particular element or our analytes is present in that sample, because normally in regulations certain concentration is still allowable, but when it goes beyond the acceptable limit, then you will see the impact either to health, either to the environmental ecosystem and whatnot. That's why concentrations is important. Okay, so now let us see the principle of how basically AAS works. Right, first let us see the basic principle. Okay, AAS is all about free atoms in the gaseous state absorbing light at specific wavelength. And imagine each element having its own favorite color of lights that is light that they love to absorb. Okay, this is what gives AAS such great specificity and detection limits, because each element absorb a unique wavelength. Okay, and the more light being absorbed at that wavelength, the more of that elements is present in the sample. That is Beer's law, right? Remember that. So the absorption's level is directly proportional to the concentration of the element. So again, this is another basic principle of AAS that have a similarity with the UVVs. Okay, elements have their specialty in absorbing only certain wavelength. Next, for sample preparation, the sample you want to analyze can be in different form. It could be in aqueous solution, which is just a solution in water, or an organic solution, which means that the sample is dissolved in an organic solvent. So you need to know if you want to test certain elements and that elements are not able to be dissolved in water, so you need to find another solvent, either it's organic, other organic solvent, for dissolving our sample in that solvent. So then the solid, as long as you can successfully dissolve it, you definitely can measure what elements contain in it. All right, next on the atomization. All right, this is a crucial step. All right, atomization is crucial step in the process where basically liquid sample get thrown into a flame. You have to make sure that that sample become a flame first. The heat from the flame convert the sample into free atoms in the gas phase. This step is essential because only when the atoms are in the gaseous state, they can absorb the light, allowing us to measure their concentration. Alright, so this is the different part that you can identify comparing with the UVVs that you've learned before. Right, remember, there is the elements of flame involved here to make sure that your sample solutions need to be ignited and forming a gas. From that gas only you can convert that sample to the free atom. Okay, got it? Now let us see how light being absorbed. Okay, in AAS we shine lights of a specific wavelength through a flame. So this wavelength is chosen. So don't worry, because later in the instrumentation I will show you how the lights is actually shine through the flame. Okay, and only after we shine lights of a specific wavelength through a flame, this wavelength is chosen based on the element we are analyzing. All right, so when the light passes through the flame, the atoms are in the gas. Okay, in the gas phase there are atoms flying over, so these atoms will absorb the ultraviolet or visible light, okay, based on the lights that we shine. And this absorption causes the atom to move to a higher electron energy levels. That important parts here is the amount of light absorbed is directly proportional to the concentration of the elements in the sample. So more absorption means higher concentration of the elements. Understand or not? Because if your solution contains a lot of copper, for example, so the copper ions or the copper atoms will be freely in the flame. So a lot of copper atoms will absorb the wavelength they love to absorb. Okay, and that will be quantified later to determine their concentration of the element. Okay, so the quantification part is achieved by producing the calibration curve for standard solution. The analyte concentration is determined from the amount of absorption compared to this standard. And finally, about the specificity. Okay, each element, I mentioned earlier in this part, each element has a unique fingerprint when it comes to light absorption. So atoms of different elements, for example copper or aluminium, they absorb a different wavelength in lights. Okay, so that's why AAS using elements specific lamp, meaning that if you are going to check on aluminium, so you have to use aluminium specific lamp. If you want to use you want to check copper in your sample, so you will use copper specific lamp. So you have to change the lamp. Another differences with UVVs. Okay, if you compare to UVVs, you only use one lamp and you didn't touch the lamp. But for the AAS, if you know what elements you want to test, so you will change your lamps according to the sample. Okay, copper sample, aluminum sample, plumbum sample. So these are the differences where your elements very specific absorbing lights, okay, at their unique wavelength. When you want to test other types of element, you need to change your lamp according to the element to be tested, right? So I hope you get it. Now let us see in atomic absorption spectrophotometer, the equipment itself. All right, so how does it work? Right, so this is a common, okay, but most probably you will be having a different setup, a different size, a different looks of AAS, but the concept is almost the same. Okay, you'll be having a sample in your beaker or in the bottle. All right, so the sample solution is introduced into the system through the sample flow inlet. Okay, all right, so you can see the pink color, okay, in the beaker where actually the sample is located, and then you have a tube sucking the sample into the mixing chamber. So the sample solution in the mixing chamber, all right, they will mix together with fuel gas and also oxidizing gas, right? So this mixture is necessary for the atomization. Remember, the atomizations means that you are producing atoms from your sample solution just now. Okay, so atomizations, it is in the flame part. All right, the mixed gases and samples are then transported to the slit burner. Okay, you can see the slit burner on top of it under the flame, okay, where they are ignited to create a flame. So in the flame, the sample is atomized. Atomized means it converts into free atoms in the gas phase. All right, so that's why even though your liquid sample earlier in a form of liquid, it will be heated and they will heat it up until the sample is in a free atoms forms. Okay, now let us see on the hollow cathode lamp. Okay, the hollow cathode lamps specific to the elements being analyzed. So either you are checking for plumbum, lead, or copper, or aluminiums, or magnesium. So you will use a different set of hollow cathode lamps, right? So it is actually being stated in the hollow cathode lamp that lamps is specific to what elements. You can see it in the lab later. So emit lights. So this hollow cathode lamp will emit lights of a particular wavelength characteristics of that element. That's why they know what lights to be emitted. If you are choosing wrong elements of cathode lamps, so basically maybe your sample is not absorbing it. That's why you have to choose which best lamp for your element to be tested. And absorption of lights. So after the cathode lamps has been actually shined, okay, the beam of lights travels through the flame where the free atoms of the sample absorb light at a specific wavelength. A slit aimed to focus the lights into a narrow beam. Okay, because after the flame it is still in a wide beam, so to make it narrow, entering the monochromato is very important. All right, so the monochromator here is basically to separate the absorbed light from other wavelengths, ensuring that only the light specific to the element being measured reach reaches the detector. So the parts on the monochromata detector and also indicator device is almost similar like what we have in the UVVs earlier. Alright, so the detector measures the intensity of the absorbed light. The amount of absorption is directly proportional to the concentration of the elements in the sample. An indicator device, the signal from the detector is sent to an indicator device. So commonly it is a computer which processes the data. The concentration of the element in the sample is calculated based on the absorption and displayed or recorded for analysis. So you'll find your results from the indicator device. Okay, so this is a simple process on how your atomic absorption spectrophotometers work. Next, let us see on the instrumentation. I will not be highlighting all. You may actually study it by yourself later, but I will highlight some of it, right? So the instrumentations involved in our AAS, basically the source of lights, okay, different types of lights being used in AAS, nebulizer, atomizer, monochromata, detector, and readout device. So for source of light, the one that I mentioned earlier is hollow cathode lamp, commonly being used, but there are also electrodeless discharge lamps can also be used, okay, and this contains for the hollow cathode lamps, it contains a tungsten anode and a hollow cylindrical cathodes. And as I mentioned again, all right, these hollow cathode lamps or these lamps is very specific to the elements that you are using. So each element has its own unique lamp which must be used for the analysis. You cannot use only one lamp for various types of your element to be tested, because you would be getting the best absorption being detected, because each element, as I mentioned, they have this fingerprint. They only loves to absorb their specific wavelength. All right. Nebulizer, it suck up the liquid sample at a control rate. So that is the initial part when you put your sample in a bottle or in a beaker. So basically this nebulizer is actually plays its role to suck up the liquid sample, all right, and it creates a fine aerosol spray for introductions into the flame, okay, and before that it mixes the aerosol with fuel and oxidant. Hopefully you are able to look back in our previous flow how the AAS processed, right? Atomizer, okay, the elements to be analyzed need to be in atomic state. It's not in a liquid state, because just now you have the nebulizer, it is in a mist, and once it is in a mist, it is actually in a form of vapor, all right, and then you vaporize it, okay, heat it up, and atomizer is to ensure that it is in a form of atom after you burn it, okay, or you flame it. So this is done by exposing the analyte to high temperature in a flame or graphite furnace. So there's two types of atomizer that commonly used, okay, either flame atomizer or electrothermal atomizer, right? So let us see how flame atomizer works, okay. So you can read all this part and look into the steps of flame from the sample. Either it is normally in a liquid form, you form the nebulizer, create a mist, and you will form the aerosol, all right, dissolve it, you volatile it and become a gas. These are all in the mixing chamber, and once it's being heated, then it start to dissociate from the gas molecules. From the molecules becomes the atoms, all right. So this is where the atomization meant for. It becomes the atom. From your sample become the compounds and then the molecules, and from that molecules it turns into atoms. All right. So this is under flame atomization. And for electrothermal atomizations, okay, you undergone the process of drying, pyrolysis, atomizations, and cleaning, all right, in the thermal atomization process. Next, monochromata. Okay, monochromata is basically similar to the one that we've learned in UVVs. Okay, it is very important part in AAS as well, because it used to separate out all these thousands lines of lights coming from the flames just now. Okay, and the monochromata is the one to select the specific wavelength of light that is absorbed by the sample and to remove other wavelength. Okay, though we have used the lights with a specific wavelength, but still yet there are other impurities that other wavelengths also present, and the specific wavelength will be separated by our monochromata. Okay, and the final one is detector and amplifier, where basically the lights emitted from the monochromata is directed into a detector whose function is convert the light signal into the electrical signal. Okay, from this, the process of electrical signal is fulfilled by a signal amplifier, and the amplified signal is then displayed on readout system or fed into a data set station for printout in a requested format. Okay, so this is the overall instrumentations in our atomic absorption spectrophotometer. Calibration. So the calibration part is basically what you have experienced in the lab for the UVVs. All right, so you are supposed to produce the calibration curve because you want to determine what is the concentration of certain elements that you want to find out in your sample. So the instrument is calibrated using several solutions of known concentration. You see on the top part you have reference one, so you have concentration from low concentration to higher concentration. All right, so you form plots. You plots a calibration curve. Okay, the adsorbent of each known solution is measured, and then the calibration curve of concentration versus absorbance is plotted. All right, and then the sample solution is fed into instrument, and the absorbance of that element in the solution is measured. So after you identified the absorbent, okay, you get a line from the absorbent into the lines created by the calibration curve just now. So the concentration of your sample is then can be obtained from that calibration curve. Okay, so that's simple. Now let us see on the applications. Okay, different types of applications is basically important for you to ensure that you are able to use AAS for a specific application. Okay, just want to highlight on various types of applications of AAS, and it is not only here what are the applications of AAS can be used for, but there are other fields of analysis can be applied using AAS. Okay, for example, water quality testing. You want to determine a certain trace metal presence in your drinking water or in wastewater. All right, for example in Malaysia, let's say if there are some places still using a metal tubing or metal pipe, and if you're aware, this metal pipe upon time can be corroded. Okay, and these corrosions will basically upon time emits these metals into drinking water, or into the water that actually being supplied to houses. And as we know, as a human being, we cannot detect the presence of drinking water, the presence of trace metal in the drinking water unless colored appear. All right, but in common cases, sometimes the color is is uh, is not observed significantly, but actually the trace metal or the metals presence in the liquid or in the water is high already. So that's why, especially those old times, okay, they use plumbum based tubing. So it releases this plumbum into the drinking water, and what happened, it is not an acute results, okay, it takes longer time, after 10 years, 20 years, 15 years. So what happened, it affects into the health of human. For example, plumbum, okay, plumbum leads into the um, what we call that, um, the growth of intellectual of a baby, okay. So it will affect, okay, if your mother or my father of a baby, all right, you keep on giving the baby, and even during the pregnancy of a woman, consuming that drinking water contaminated with plumbum, okay, with lead. So what happened, the baby that actually affected, okay, and they have low intellectual level, okay, because of this plumbum. So you just imagine, this is very important, we need to check, okay, not everyone, but once it need to be detected. And also, in a case of manimata, have you come across the manimata diseases in Japan? It is in 1950s. I am suggesting you to just check on manimata diseases Japan 1950s, where there are cases of mercury poisoning in a Manimata Bay, Japan. All right, it release, actually the industry near to the river is actually dumping their waste to the Manimata Bay. So what happened, this mercury is actually methyl mercury taken up by the fish nearby, and human being consuming this fish, okay, they eat the fish, and this fish is contaminated with methyl mercury. And mercury itself is bioaccumulated in fish and shellfish, okay, shellfish. So when it consumed by the population nearby, it leads into severe neurological damage and also death, okay, it can become a death threat, okay. So many death cases is actually being reported from this Manimata. So the identification of mercury contamination was crucial in linking to the factory. So they want to find out who's the culprit actually dumping this mercury. So only then they find out that the company close by is actually, they are not using, they are not applying appropriate method of disposing their waste, but they just dump through their river next to their plant. So this is a very bad one, which affected the population of Manimata. All right, there are a few cases as well. For example, in Malaysia, okay, in Malaysia, you remember the Pasir Gudang chemical spill, the Kim Kim River in Pasir Gudang, where the spill released toxic fume that affected thousands of residents and led to the temporary closure of schools, right? Various schools has been closed because the fumes coming out from the dumping of waste into the river. Okay, remember, when you are working in an industry, you have to make sure that the industry comply to the waste management procedure. All right, if the company is actually dumping their waste to the backyard, to the other people's or the public compound, so they are not doing correctly, okay, they are not comply to the regulation. So not only the management will be fine, okay, not only the company will be fine, the management will also have to take the responsibility, okay, either being jailed or whatsoever. And if happen to be you are the one in the management of the company handling on the safety and waste management process, you will be the one behind the bars. Okay, so it is not a threat, it is an information for you to ensure that all the industries comply. Not only industries, but sometimes us, when we find that this is the one that we are discharging having impact to the environment, to the human health, so we have to follow the rules, okay, make sure we discharge our effluent accordingly. All right, in nutritional content also, you will find out either the one that always claim, okay, we have ferrum in our food product, okay, so how much of that, so you can actually track through the AAS. Okay, some they claim they have high content of certain elements which gives a better what we call that, better output for those consume it. But when it is detected, okay, it is analyzed, the compound sometimes is not present, it's just an artificial claim which is wrong. All right, so in pharmaceutical analysis, for example, you estimate the zinc in insulin preparation, calcium in calcium salt is done by using AAS to ensure. Okay, even in gunshot residue analysis to determine the elements like plumbum, antimony in gunshot residues. Okay, those works in this field. Okay, you can identify these elements using AAS. All right, so that's it. So I hope that by now you find all the instrumentations through different types of techniques in analyzing the samples or analyzing the elements, okay, that you've learned so far benefits you and interests you. Right, so that, thank you very much. Okay, these are the references used for this literature, for this lecture. I wish you all the best. Okay, I'll be uploading the assessment of our lectures throughout these weeks, okay, in e-learning. With that, thank you very much. Assalamualaikum warahmatullahi wabarakatuh.